Okay, last time we have been discussing about the attitude dynamics. So, we continue with the same topic. Okay. So, we looked into the active and the passive controls. In the active control, we had the rocket control, the reaction wheel control, then dual spin satellites, the spin satellite we saw, while the passive control was the gravity gradient control. So, but the gravity gradient control it is cheaper, easier to design, but what happens it is a pointing accuracy is very poor, it is around 10 to 20 degree. So, gravity gradient control pointing accuracy 10 to 20 degree. Okay. So, it is not good, it may assist. Okay. You can design a satellite where the reaction wheels other things are available, and you have to make a earth pointing satellite. So, in that case it can assist, if provided you design your satellite in that way. So, many of the satellites may be designed like, say you have a satellite here which look like these are the solar panels. These are the connected solar panels, and you may have a gravity gradient boom where a mass is attached to a, this is the boom, and one mass is attached to that, and instead of there being a mass, you can have certain instrument stored in this, if this is heavy. Okay. So, this will provide you the constant gravity gradient. So, this will assist in stabilizing the satellite, which will and where you are designing it to always point toward the center of the earth. So, this is called the favorable gravity gradient in this case, because it is favoring it to stabilize it. But as a whole, using just the gravity gradient control satellite for our various scientific purpose, it is not feasible. Okay. You can see that the accuracy is not very large, moreover the orientation other problems are there which you must do. So, therefore, either we have to do the rocket control, reaction wheel control, these are the active controls. Okay. Other thing like the spin stabilization, those are only for the stabilization purpose, but if you have to change the orientation of the satellite, so ultimately you have to come down to the using the reaction wheels or the rocket motors, or what we call as the magnetic actuators. So, in the magnetic actuators we have 3 coils. So, this is one current carrying coil, and another current carrying coil will be perpendicular to this. Okay, another will be lying like this. So, these are in 3 different planes. So, we can assume that the center is here. So, this is one face of the coil, this is another face, second coil, this is the face of the third coil, and these wires they carry the current. So, if this is put on the satellite on board, and the satellite is at low altitude, say up to 700 degree 700 kilometers, okay, 300 to 700 kilometers. So, as we go up, magnetic field of the earth it dies out fast. Okay. So, magnetic field of the earth it is directed like this. Say if our magnet is pointing to you, if the north of the magnet and this is the south of the magnet. Okay. So, it will point toward the magnetic south of the earth. Okay. So, earth is basically acting as a big dipole, this also is acting like a magnet. Okay. So, naturally if you have a artificial magnet or the, and if you hang it about this point, so it will try to orient like that only. So, in that case this will be pointing you the south, magnetic south. So, the north pole of the earth, which you call the geometric north. So, that is basically the magnetic south of the earth, because here the north pole will only orient towards the south pole, and south pole will only orient toward the north pole of a magnet. So, earth can be assumed to be a big magnet. So, in this magnetic field, if your satellite is moving, okay, so you have the magnetic field which is spreading like this, and let us say coming and terminating over this pole. So, if your satellite is interacting, these coils are interacting with this, and these are carrying currents. Okay. So, they will produce dipole moment. So, this also these coils, they act as the dipole, okay, and we are not going to get into the equations for them, but you assume that these are acting as a dipole, and therefore, once they are interacting with the magnetic field, a torque will be produced. So, at any time in the case of the magnetically actuated satellites, only 2x control is possible at a particular instant of time. So, again we need not go into the details, but it will be suffice to say that over a period of time, 3x control is available. So, the torque is written as the dipole moment cross the magnetic field. Okay. So, whenever the magnetic field it coincides with the it is parallel with the dipole moment. So, no torque will be produced. So, we have the 3x coils here. So, one of them will be coinciding with the, or say that the one of the component of the total magnetic field total dipole moment, these 3 coils constitute. So, one component will always lie along the B vector, and that it gets neutralized. So, only 2 components are available, and therefore, we say that the only 2x control is possible at a particular instant of time. So, only 2x possible at any instant of time. However, over a period of time 3x control is available. So, as the satellite is moving in the orbit, okay, around the earth, so 3x control can be carried out. So, for small satellites this is very advantageous, and nowadays when the micro, nano and pico satellites are being designed. So, in that case it can be utilized, and it is a low in cost, easy to design, okay, and say also reliable, also active control can be done using this, but few limitations are there, that if the satellite is rotating at a very high speed, it is not feasible to use this magnetic actuators, because it can control the satellite at lower angular velocities, at lower rotational rates. Okay, so, this is our description of magnetic actuator control. So, this is enough background for our purpose for this course, because we are not going into the only 6 lectures are assigned for this particular topic. The rest of the things we devote over the attitude dynamics. So, now we consider the rigid body dynamics. Suppose this is an inertial reference frame and we have another reference frame E 1, E 2 and E 3. This is a rotating reference frame. Some rigid body is there and this is the center of mass of the rigid body. In this point, let us write this point as A and this point we can write as O. The angular velocity of this rigid body, let us say it is shown by omega, where omega is a vector whose components are omega 1, omega 2, omega 3. So, omega can be written as omega 1 times E 1 plus omega 2 times E 2 plus omega 3 times E 3. So, this body is rotating at the angular velocity with angular velocity omega. Okay. Now, what we need to do here, describe the rotational motion of the satellite. Okay. So, for describing the rotational motion of the satellite, we need to proceed from scratch and work out the whole thing. So, let us say that the radius vector of the point O, this is r 0 and there is point in the body whose radius vector is rho. So, the distance from here to here, this can be written as r. So, while we are working with this the rigid body dynamics, so we will utilize the results developed in the few lectures that I gave at the start of this course. Okay. So, O is the center of mass of the rigid body and also origin of the reference frame E 1, E 2, E 3. E 1, E 2, E 3, these are the unit vectors. We can write it as x, y and z, and the unit vectors in these directions are E 1, E 2 and E 3, or either we can remove this altogether and we can imagine that E 1, E 2 and E 3, these are the 3 axes, and E1 cap, E2 cap and E3 cap, these are the unit vectors. So, E1 cap, E2 cap and E3 cap are unit vectors. Similarly, E1 cap, E2 cap and E3 cap, these are also are unit vectors, and the axes are E1, E2 and E3. So, here we should the reference frame we should remove the cap here, because that indicates the unit vector. Rho is the position vector of the point. Let us say this point is P, point P with respect to the center of mass. So, angular momentum of the small mass, there is a small mass which is located here in this point. So, let us say its mass is d m. Okay. So, the angular momentum of the small mass d m located at P can be so, for the angular momentum of the body, the small mass P, that I need to find it out. So, angular momentum of P or the mass d m about the point O can be written as d h is equal to rho cross v times d m, where we will see that we are finding the angular momentum about this point. So, this is the moment arm, and suppose our velocity v is directed like this. For this particular mass, this is the velocity direction v. So, if this is the velocity direction, so rho cross v multiplied by m, that represents the angular momentum vector. And v obviously can be written as the velocity of the center of mass, which is v naught plus omega cross rho, and this we have worked out in our the few initial lecture at the start of this course. So, if we integrate this we have to multiply it by d m here, and if we integrate it, we get h. Now, this can be written as rho d m times v 0. This is the cross product. Okay, this is the cross product here. This is also cross product plus rho cross omega cross rho d m. So, now if O is the center of mass, so this integral will vanish. So, this integral, this quantity, this equal to 0, because O is the center of mass of the body. So, this quantity as a whole, it is not contributing to the angular momentum of the body. So, what we are left with H is equal to rho cross omega cross rho So, this is a cross product and the this can be written as rho dot rho times omega minus rho dot omega So, therefore, H will be now we can expand it and write in a proper way. So, we can write rho equal to rho 1 E 1 plus rho 2 E 2 plus rho 3 E 3 and omega already we have written in terms of omega 1 E 1 plus omega 2 E 2 plus omega 3 E 3. Remember this omega, these are the components of angular velocity along the body axis. So, in this figure this is the velocity vector omega. So, we are taking the components of this velocity vector along the direction E 1, E 2 and E 3. Similarly, this rho vector its components are taken along the E 1, E 2 and E 3 directions. Now, we define the diode as this diode is defined as the product of two vectors without considering dot or cross product. So, if we write E 1 times E 2, so this constitutes a diode. So, now we define a quantity what is called the dyadic. So, this dyadic will be the summation of such diodes. So, if we write E 1 E 2 plus E 1 E 1 times E 2 E 2 and assign this the symbol E double bar. So, this is called a unit dyadic. Now, we will utilize this to rewrite this equation. So, we can number this equation as A So, E double dot W bar we can see that this can be written as E 1 plus okay. So, this will get reduced to omega 1 E 1 if we take the dot product. which is nothing but omega. So, if we are taking the dot product of a vector with a unit dyadic, so ultimately we get the same vector. So, if we utilize this property, so in equation A, we can write H equal to rho square omega minus rho times this is the dot product omega dm. Okay, now the omega we can replace in terms of a dyadic. Okay, so writing this as we have written is E double bar dot omega sorry, this is not a dot product here, this is not a dot product, simply a multiplication here in this place. So, rho square omega, because we are taking it from this place. So, this rho, these two vectors multiplied together, this becomes rho square and there is no dot product. So, this was just a point I indicated. So, I have removed now. Now, if you look into this equation, omega dot can be taken out of the integration sign, because integration we are doing with respect to the mass, not with respect to the omega. So, therefore, we can write this as rho square E double bar minus and this multiplied by omega, and here the dot we are bringing in. So, ultimately H can be written as where I double bar, this is called the inertia dyadic, inertia Okay, once we have done this, so this H, this H can be expanded and it can be written in a format. Okay, inertia dyadic, let us first write this further. First we will do this and then we will come to the expansion of the H. So, this can be written as I alpha beta times E alpha cap and E beta cap, where E alpha cap and E beta cap, these are the unit vectors. The unit vector. Okay, so, basically this is written in a tensor notation. So, inertia tensor can be, this inertia dyadic can be written as I 11 E1 cap, E1 cap, I12, E1 cap, E2 cap, and I13, E1 cap, E3 cap. Similarly, other terms can be filled in. So, and this is basically symmetric. So, this also becomes I12, E1 cap, E2 cap, I22, E2 cap, E2 cap, and I23, E2 cap, E3 cap. Similarly, here in this place we will have I13, E1 cap, E3 cap, I23, E2 cap, E3 cap, and I33, E3 cap, and E3 cap. So, this is your inertia dyadic, and what you are doing, you are writing H as the product of this inertia dyadic. So, in the matrix notation, the same thing, this thing you need to place here in this place, and your omega is omega 1 E 1, you write omega 2 E 2 in this way, omega 3 E 3. Okay, take the matrix product and you will get the result for H. So, H 1, H 2 and H 3 components you get it from this place. H can be expanded, and finally, you can write it in this way. Okay, now one thing more, this the you can put the sign here. If you want, you can put a negative sign here before the I12, and here you can make minus I13, and similarly the negative sign before these off diagonal terms. So, why I am suggesting that? Because once you write the cross product of inertia, say you write I x y. So, this is x y times the mass. So, here if you write it in this way, then you need to put a negative sign before this, but if you absorb the sign in this place, then you can keep the positive sign here in this place. So, if you are keeping a negative sign here in this place, then all these terms will turn out to be positive with positive sign. Okay. If you make this as positive, so here the off diagonal terms they will have the negative sign. So, it depends on the choice what kind of representation you want to do. So, let us make this negative. Okay, so, all these off diagonal terms are negative. So, the cross product this is the diagonal term, this is off diagonal term, and this is okay. So, here we have the negative sign here in this place, this place. So, the only the diagonal terms will not have any negative sign. So, similarly, so in this case you have I12. So, I12 you will be writing as the rho 1 rho 2 times d m, where rho 1 and rho 2 these are the components of the row vectors, and because you have absorbed the negative sign here in this place. So, all this will contain a positive sign. So, ultimately the equation we showed here in this place, this particular equation, you can expand it in terms of these vectors and do the integration and get the result. So, maybe we will postpone it little bit toward the next step, and we will right now see the results and later on work with the more details. So, right now our concern is with looking into the configuration, how does it look like. So, this is I 1 2 omega 2 minus I 1 3 omega 3 . This is I 1 3 I 2 3 because it is a symmetric. So, we write in the same way. You see this I 1 2, this indicates your integration rho 1 times rho 2 d m. Okay, and similarly I 2 1, this indicates the integration rho 1 times rho 2 times d m. Okay, so, there is no difference between this. So, I 1 2, this is equal to, this is identically equal to I 2 1. So, in the matrix notation you can write H 1 H 2 H 3 . Okay. Now, we have got this. So, this is your angular momentum equation, and this is your angular momentum vector whose components are shown here. Now, before we do anything further, let us look into the some of the properties of this real symmetric matrix. So, 34 properties of real symmetric matrices. We are going to utilize these properties in developing the equation of motion. So, all real symmetric matrices eigenvalues are real. So, you may wonder what does mean by the eigenvalues of this matrix. Okay, in MATLAB there is a command EIZ. Okay, so, if you have a matrix, if you type a matrix in the format, say a matrix you define as A, where the components of this matrix are written as something 10, 10, 20 and 5, and they are separated by this semicolon, and then you can write as say 5, this is 10, 20 and 5. So, this is the symmetric matrix will be, this will be 20, and then let us say this is again 20, and the last term is 30, then again separated by a semicolon, and then it is a 5, 30, and let us make this as the 15. Okay. And if you give in MATLAB this command EIZ A, so it will give you the list of the eigenvalues of this matrix. So, this is the moment of inertia matrix, these are the diagonal terms and the off diagonal terms. So, off diagonal terms are nothing but basically the product of inertia. So, the eigenvalues of this matrix, it signifies the principal moment of inertia. Okay. So, it is a possible that if you diagonalize this matrix, so you get the principal moment of inertia, and the corresponding eigenvectors, they indicate the direction of this principal moment, principal moment of inertia direction. So, in which direction it is lying, so that direction you can obtain with respect to certain x. So, we list the first property as the eigenvalues are real. So, eigenvectors eigenvectors of a real symmetric matrix can always be selected as real. A real symmetric matrix is always diagonalizable. So, a real symmetric matrix is always diagonalizable. So, what does mean by diagonalizable? That if you give this EIZ A command, if this is obviously here this is a real symmetric matrix. So, if you give this command, so you will see that this matrix is having only the diagonal entries, these 3 entries, rest other entries are 0. Okay. So, this implies diagonalization. So, only a real symmetric matrix is having this property that it is always diagonalizable. So, every real symmetric matrix has a complete set of orthonormal eigenvectors. So, in this case this matrix, this is the inertia matrix, and because this is real and symmetric, therefore, this will have 3 orthogonal or orthonormal eigenvectors. So, if you have a matrix A, so A transpose A, if this is written as I, so you call this as the orthonormal. So, now we take the next property. for every symmetric matrix A, obviously here we are considering matrix of size n into n, the n rows and n columns. So, there exists an matrix of size, a matrix of size, a matrix M, which is again of size n into n, which is a real orthogonal matrix, okay, such that M transpose A equal to D, where D is a diagonal matrix. These two matrices are orthogonal if A times A transpose equal to I, we can put here in this bracket. So, this is orthogonal, we write orthogo. And if two vectors are orthogonal, okay, so two vectors are orthogonal means they are perpendicular to each other. So, there will not have any component of this in this direction. While in the case of the matrix we write this, that if they are orthogonal, then they have this property that A times A transpose equal to I. And you can see from this property that if A times A transpose, this is equal to I, so A transpose, this implies that this is equal to A inverse. So, if we take the product on the right hand side, like if we write A transpose A, so this become A inverse A, okay. And A inverse A is nothing but your identity matrix. This is identity matrix, I is a identity matrix. You should not confuse this with the inertia matrix. So, we have seen that the orthogonal matrix, it will satisfy these two equations what we have written here. So, next we go to the next property. So, the matrix M, this is called a modal matrix whose columns are the eigenvectors of the matrix A. D is a diagonal matrix whose diagonal entries are the eigenvalues of of the A matrix. Eigenvalues in the modal matrix, eigenvalues in the diagonal matrix are in the same column as their corresponding eigenvectors in the modal matrix M. So, with these 8 properties, we will be able to analyze the inertia matrix. Okay. So, we will list few other properties also. So, if we are given the I matrix, which is the inertia matrix, so we can list 3 principal directions of this, which will be corresponding to the 3 principal moment of inertia, which will be corresponding to the diagonal elements of this. So, we have again a eigenvalues of the moment of inertia matrix is the principal are the principal values, principal moments of inertia. Okay, if this happens, so if your matrix gets diagonalized, the inertia matrix A, which we have been earlier using with notation A. Okay, so if your inertia matrix is diagonalized, then the off diagonal terms will become 0. Off diagonal terms of the diagonalized I matrix, which we have indicated as D earlier, will be 0, indicating absence of product of inertia terms. Okay, one important thing you should note down, that the principal directions, the principal moment of inertia, the principal moment directions and also inertia depends on the point of consideration. So, if you take any body, so if you are considering what will be the principal moment of inertia about this point, okay, so it will be different, and the corresponding principal moment of inertia direction will also be different. If you consider another point which is located here, so principal moment of inertia will again be different, okay, and the corresponding direction also becomes different. So, this is a very this is the characteristic which need to be taken care of while developing the equation. So, we stop here, and the next class then we will start developing the equation of motion. Thank you very much.